Hi and welcome. This is the last lecture of the projectile motion lecture videos. In this lecture, I'm going to look more and focus more on the projectile launch at angle type problems. They need a little more analysis because we have vector components of the velocity. And the other thing I'd like to look at is the angle. How does the angle affect the range, the time, and the maximum height of all these types of problems? Lastly, I'm going to derive what is called the range equation, a very helpful and useful equation to solve for the range given the launching velocity, and I'll show you how to do that. So one of the other things that comes about when you solve projectiles launched at angles is that when we launch this object with this velocity, so I'll just take this as a problem very briefly, or actually even better, I have it kind of loaded up here. So right now I have an object and we're going to launch it. The initial speed is 18, so there you go. Fired a piano today. I didn't plan that, but I hit the target. But anyway, let me just erase this and fire it again. And what you can see is that this motion, when it first starts out right here, is going to have two parts. The object's not only moving upward, but it's moving over, so it's moving from here to here. And that's what this line represents, is the two motions combining like that. So because of that, the velocity right here, what we have to do in order to solve problems is actually take out each component. So if you notice in the other lecture, I was talking about how we solve problems with x and y like this. Well, in order to use Vx is equal to dx over time, and that delta y is equal to Vit plus 1/2 gt squared like this, notice that these are all y and x velocities. So when you launch an object to begin with, I'm going to use a blank page, such as this, and you know, it goes like this, more or less. Bad drawing, but you get the idea. This velocity has both x motion and y motion combined. And notice, in order for me to make this angle, I have to go right and up. And that's exactly what this object's doing at that point. So the first step to solving projectile motions is to find your initial Vx and Viy. This is always our starting point. Now the reason we have to do this is what I was describing earlier, is remember our equations use these values, so Vx, so Vx, Vx. That's why we're doing this. The problem is if you use this, it doesn't model the x motion. It models both x and y. So I'm going to write this as a vector. So we have Vx x hat plus Vy y hat. Now this is the calculus version of saying exactly what I said over here, is that we have to go in the x direction and the y direction. And this vector v here represents the two of them. So this is just a mathy way of saying exactly this right here, Vx and Vy. So when we solve vectors, notice that we're making triangles here. So usually we'll have an angle right here. So we can actually solve this using any sort of SOHCAHTOA. Sorry. I recommend that you kind of stick to the same thing. So if you notice here, using SOHCAHTOA, this is the adjacent, this is the opposite, and this is a hypotenuse. So to find the Vx part here, notice that's an adjacent. So that's the k of the SOHCAHTOA. That says cosine of the angle is going to equal to the adjacent over the hypotenuse. So now what I'm going to do is plug in the values for our triangle here. So this is really going to be cosine equals the adjacent, which is Vx, over the hypotenuse, which is V, And then if I solve for Vx, I multiply V on both sides. So what we get is V cosine of the angle is going to be our Vx. So this gives us the ability to solve problems now with x in the component right here, just like that. Now with the same logic, I could do it for the y. The y is the opposite piece, so that's going to be the SO of SOHCAHTOA, which is the sine opposite over hypotenuse. Now I'm going to plug in our values, sine of Vy. Now I'm going to go ahead and just put an I here to represent this as the starting velocity. Now the y velocity changes, so this is exactly at the start point. And then notice the same logic. I got to multiply V on both sides. I can get Vy as Vi sine of the angle like that. So when you see stuff like this, this VIY, you're going to plug in the V sine of the angle. Whether you plug that in as a variable here or you solve this and plug that in. But that's what that represents. And same thing, this is Vx cosine of the angle right there. So let me go back for a second. And this is what this is showing you. It's saying, hey, look, in order for this object to go this way, you're going to have to move this horizontal way and this vertical way. So these are called components, and when we take the velocity and we break them down into components, that's called resolving the vector. And that's exactly what this slide is telling you. It just comes to the end point right here. So this angle is theta right here. That's what this is. So this would represent the number that goes in here. So the other thing is to notice too is that I have the symmetry going on here, meaning that if you do one thing on one side, it's the same as the other. So that's a really helpful way to solve problems. Now, the Vx is constant, so no matter where we are on the trajectory here, Vx will always be 5 meters per second. But notice it's the y velocity that changes. It starts off fast, and then stops, and then it gets slower. So it's not mentioned up here, but you can definitely use 0 as a component. Same thing, if you know the time up, you'll know the time down. Let me show you a couple features on this program here. So I'm going to go ahead and play with this program and show you some of the things that you should recognize here. So I'm going to change the angle every time. I'm going to start off at 0. So this is actually not officially on the ground, so this will fall a little bit, but technically if I had 0 angle, this should just go straight. But we see that it does fall a little bit there. So it's a little off. So I'm going to go up by 10 degrees. Oops, let me start over. I want to take off air resistance. So here we go. And 10, 20, 30, 40, 50, 60, 70, 80, 90. Okay, so the big thing I wanted to show you here is that notice, in the beginning, this is 10, 20, 30, 40. We have the maximum amount of, we have a greater range, right? In fact, if I go exactly 45, that is the key number. That's the maximum range you can get. Now, the reason is because you have just as much velocity in the x as the y, because remember, a 45-degree angle 45-degree angle has equal sides in x and y. So this is 1, this is 1, this is square root 2. So with that said, you have a lot of component of the horizontal component, which allows you to go all the way over here. So you get max range at 45. And take a guess at where your max height. So you get max height at 90 degrees. Now the reason for that is because you're going straight up here. So notice that when you're at 90 degrees, you get the maximum height. And then notice if this were a perfect world, we'll actually see that if we launch this at, this is not drawn to scale, 20 degrees, and we launch this at 70 degrees, we'll find that the ranges are same, like that. So they don't actually line up because, like I said, this is actually not at 0. But if we did see that, we see that they line up to their correspondent. And if you notice, it has to do with their symmetry. If I added these two up, it has to do with 90. So another pair would be 60 and 30, like that. Sorry, that would be 30 and then 60. So these angles that add up to 90 will always have the same ranges like that. But the difference is the 60 will take longer to do that and will go higher, as you might imagine.